welcome everybody to Mingo Creek Park Observatory, as we know as MCPO, one of two amateur observatories in our club. The other one's up in Deer Lakes Park called Wagman Observatory. I'm on that observatory staff, but I come down out here to help out. On the north side of Pittsburgh, near the Steelers Stadium and the Carnegie Science Center, something remarkable is happening. A company's been formed to build spaceships. What's Pittsburgh? It's steel mills and aluminum and glass and iron. There's a company called Astrobotic, a spin-off of CMU that's building spaceships. Never thought it possible around here. This story is about one of the newest spaceships we're building. It's called Griffin. I'm going to walk you through the mission to the moon, and you'll find out some remarkable things happening in our own neighborhood, because Pittsburgh is becoming a high-tech town. And now what's the title? As you can see, is There's Water in Them Thar Craters. And you'll see the context here pretty soon. So hopefully no technical glitches, and I'm going to start us off here. Before we go forward in time, we're going to go backward in time to the 1840s. Suddenly word got out there's gold in California. Gold nuggets you can practically pick off the ground. So 300,000 people rushed there from 1849 to 1854. That's where the term 49ers come from, the football team. 300,000 people in that area is like 10 million people today. So they used pans. You see the guy sieving. He was going through the soil in the water and looking for chunks of gold, and they found a lot of gold. And when Mark Twain, the famous author, saw this, he said, there's gold in them Thar hills. Well, we have a new water rush of gold. If Mark Twain were alive today, he would say, there's water in them Thar craters. And water is way more valuable than gold on the moon. So for hundreds of years, astronomers believed the moon was bone dry. How could there be any water on the moon? There's no atmosphere, low gravity. The sun would boil it off in an instant. Then in 1961 said, hey, wait a minute. If big asteroids hit the moon billions of years ago, and these asteroids were rich with water, what will happen is they'll land in the middle of the sun and the water will boil off. But if they land at the poles where there are shadows, the water will be retained. As a result, we now suspect that on the south pole of the moon alone, you see those craters? They never see sunlight, is maybe 10 million tons of water left over from impacts billions of years ago. See those craters? Always in shadow. Prior, in the last couple of decades, we've been trying to find out if that water is really there. We've done a lot of what's called remote sensing, satellites that orbit the moon and try to get a feel for whether there's any water, any signatures of water. But there's no substitute for actually holding onto the water in your hands. So that's when we get into today's program. Water on the moon means everything. If you have water, you have, of course, water for drinking and bathing, making food, producing air, growing plants, medical procedures, construction, HVAC. And most importantly, if you have water on the moon, you can get to Mars very easily compared to the Earth. Water is way more valuable than gold on the moon. So NASA wants direct proof of the water, something you can hold in your hands. And so they developed a program called Viper Lunar Rover. Viper will be built by NASA, and Pittsburgh-based Astrobotic, just up the road from the Steelers Stadium, will build a rover called Griffin. It's due to launch at the end of this year. It might slip into next year. Again, here in Pittsburgh, of all places, we're going to be building a moon lander. Astrobotic itself is a startup company, new technology. A lot of CMU graduates said this company would not be there if it wasn't for Carnegie Mellon University and the Robotics Institute. They started out with a handful of people in a garage in Lawrenceville, and today they have 300 employees. And in fact, they're growing so fast that they're buying up buildings on the north side to spread their work. Very nice people. So we're going to go into this mission called Griffin 1. On the bottom of that picture are the moon lander. Astrobotic is building this. NASA is building that rover that's sitting on the back. The Griffin moon lander is like a flatbed tow truck. You see them around carrying one car in the back. There's Viper on top of the lander. There's Griffin on the bottom, the actual truck. We're going to land at a site near the south pole of the moon called Mons Mouton. Griffin, it turns out, is a mythological creature from Greek mythology. It's an eagle in the front and a lion in the back. It's a mashup of two animals that can never get together. It's meant to symbolize strength and power and prestige. Mons Mouton, the landing site, is named for Melba Roy Mouton, who was a gifted NASA mathematician. She was one of the really bright people at NASA. She worked on early orbits of satellites and led a group of human computers. When the word computer came out, it was not a machine, it was a person. And she led that group. So they renamed this mountain on the south pole of the moon for her. Okay, we're going to look at the design of the lander and the rover. Now again, you'll see a lot of call-outs and technical details. I'll only show you a few highlights so I don't waste your time because we want to get you out there observing. Here's our Griffin moon lander. It doesn't look like a moon lander. First thing you notice, you see these blue panels. They're solar panels. They're facing sideways. They're not facing up. Look around Pittsburgh or anywhere in this area. Solar panels generally face upward because that's where the sun is. On the south pole of the moon where we're going, the sun hugs the horizon all the time. So we have to get our sunlight sideways to make electricity. Again, I'm not going to bore you with every last call out on here. We've got 5 engines, 5 main engines, run on hypergolic fuels, antennas, radiators to shed heat, and a big conical section in the middle to mount onto the rocket that's going to take us to the moon. I'll tell you about that rocket in a few minutes. 4 large fuel tanks, not made of metal but carbon fibers to save weight. Spacecraft have to be as light as possible. The engineers say you add lightness to a spacecraft because the more weight you reduce, the longer the engines can perform. Just like a car. A small car gets better mileage than a heavy car. Okay? Once our lander's in space, it has to do a dance. And here's the dance. I've got my solar panel, so I want to dance so the solar panels get sunlight. But wait a minute. I want to dance so that the radio antenna points at Earth. But wait a minute. I have to point towards the moon to fire the rocket engines. But wait a minute. I have to know where I am in space, so we have to point at a star. So this spacecraft, with crazy software, is going like this through space all the time, adjusting, so that we get good communications, good solar energy, aiming for the moon, and locking onto a star. So it doesn't just fly through space like this. It's always doing this, always adjusting. The Viper Lunar Rover. Again, a lot of technical detail. I'm not going to walk through all these. I want to draw your attention to that mast sticking up in the top center. It's got 2 headlights. Why do we have headlights on our rover? The rover is going to go into a crater that has no sunlight. So we have to turn on the headlights in order to see where we're going for the testing. And it has cameras and all sorts of neat devices. It's about as big as a golf cart and it costs $200 million. But what makes this rover special is not the headlights, but a big drill assembly in the middle. It's called Trident. Basically, it's a drill that just digs down into the moon's dirt about 3 feet through the ground, pulls up a little pile of dirt and lays it on the surface and does scientific measurements of that. That's this rover's job. The rover has 3 neutron spectrometers. I don't know what a neutron spectrometer, how it works. I don't know. But I do know that it's like a bloodhound. What are bloodhounds famous for? Sniffing it, extreme sensitivity. When a bloodhound sniffs something, they are sniffing for certain chemical signatures. That's all these instruments are doing. If there's water in that dirt, those neutron spectrometers go ding, 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 we found water, and report that to mission control. This is a nifty little lander, again, about the size of a golf cart. It can go 0.45 miles an hour, not real fast. You can also do what's called crabbing. Do you all know what crabbing is? I'm going to crab for you, okay? You can move sideways to avoid hazards. It can also go up about a 15-degree slope, but maybe 20 in an emergency. This is a dumb rover. What do I mean by that? If there's a rock ahead, it's going to go right into it, plow into it. It does not have AI. It can't do hazard avoidance. We control it from the ground, which I'll tell you about later. But a nifty little rover is being built in Texas, not here in Pittsburgh. And our ride to space is the Falcon Heavy rocket. It's our ride to the moon. Very big rocket. It's the 2nd most powerful operational rocket in the world. Look at there. It's almost as tall as the Statue of Liberty. Has 27 engines on the bottom. In fact, they just launched a weather satellite with it. Go on YouTube and you can see this thing flying. It's made by Elon Musk's company, SpaceX. We need the big rocket because our lander and rover is 13,000 pounds, the largest lander to go on the moon since the Apollo era. Okay, getting ready. First thing we've got to do is mate the rover to the lander. So imagine you're in a clean room right here. lower it down, bolt it down, connect all the cables, and ready to go. I'm particularly proud of this slide here. It took a lot of work to put that together. There is Viper being attached to Griffin. Remember, Griffin, flatbed truck. Then we do what's called encapsulation. All that means is the nose cone comes in two big halves. They close around the lander, and we're ready to attach to the rocket. There's our moon lander down there, kind of small compared to the payload shroud, but ready to be closed off. And once those clam shells come together, that's the last time we see the rover with our eyes or can touch it with our hands. Okay, we're going to roll out to pad 39A at Kennedy Space Center. What's famous about this pad? It's where the Apollo 11 astronauts took off. That pad is still there. It's now owned by SpaceX. It's where Neil Armstrong, Buzz Aldrin, and Mike Collins took off for the moon. So we're launching from the same pad as the Apollo 11 and a lot of other Apollo missions. Seems appropriate for going to the moon. Okay, now it's mission time. We're going to take off. We blast off on the Falcon Heavy rocket. If you're ever in the Kennedy Space Center in Florida, try to time your visit for one of these rocket launches. Your ears will be ringing when you're done. You'll be hyperventilating. It's quite a spectacular sight. So in the lower atmosphere, we're running all 27 engines. We've got a core stage in the middle and two booster stages. It can put, I think, 52,000 pounds into Earth orbit. Okay, at some point in the atmosphere, the booster stages on the side run out of gas and they're jettisoned. And you can see this on YouTube. They recover those stages, and both of them come down like this and land on their landing gear. It's a spectacular sight. Watch it on YouTube. The center stage, at some point, it falls off. It's got a trickier job. It has to land on a barge that's pitching in the Atlantic Ocean. But they figured out how to do it. See, Elon Musk is saving his rocket stations. That saves costs. Okay, once we're in space, we're still firing the upper stage engine. We throw off those big panels I was telling you about, the encapsulation nose cone. Now Griffin is exposed to the space environment for the first time. So what happens is we go around the Earth about 3/4 of the way. By the way, I'll tell you about that orange blob in a minute. I'm going to leave you kind of guessing what that represents. Engines are shut down. We fly around the Earth, and at some point, Mission Control says, go for the moon. We fire the engine on the top. See the engine firing on the top there? And we start heading out for the moon. At this point, Griffin separates from the rocket stage, and it is truly on its own. It has to rely on its own batteries and computers and engines to survive. There's a belt of radiation around the Earth called the Van Allen radiation belt. It was discovered after the first US satellite mission in 1958. This is where the electronics in the Viper and Griffin are get fried. Very intense radiation. They're designed to withstand that, but we don't know for sure. If we make it through that radiation belt, we'll go for the moon. Astronauts have to go through this. Every flight to the moon, you have to pass through the Van Allen radiation belt. Now what happens is that this far out, the moon's gravity is superior. It pulls the lander and the rover towards the moon. It comes flying at thousands of miles per hour. And then right there, we fire the engines to slow down. But you notice we're going into an egg-shaped orbit. We're not just going to go in a tight little circle around the moon. That's orbital mechanics. Again, I could bore you to death with how it works. It's to save fuel. So what we do is we shrink that orbit from a big ellipse to a smaller ellipse until we're orbiting the moon. It takes a couple of days, but you save a lot of fuel in the process. Go for landing. Mission Control in Pittsburgh, Astrobotic, that's where the mission control is. They say, go for landing. Here's what happens. We fire the engines twice. Once to start falling out of orbit. We're in free fall towards the moon. That's called the deorbit burn. Then we fire the engine a second time for the landing burn. We don't want to burn the engines all the way down because we'll run out of gas. The biggest risk any moon mission is running out of gas before you land on the surface. It's happened about 5 times to other countries' landers. As we get closer, we've got to make sure we're where we want to be. So we use something called terrain relative navigation. And all that is, there's a picture of the landing site on the onboard computer and a camera. The camera looks for that site and matches images. See the two? One is the view from the camera, one is in the computer. When they line up, you can land on your landing site with an accuracy of 300 meters, which is astounding over a distance of 250,000 miles. Incredible landing accuracy. Oops, I'm going to do that again. As we get closer to the moon, we turn on something called LiDAR. LiDAR is the light version of radar. We turn on laser beams, and we sense the surface. It tells us how fast are we coming down too fast, coming down too slow? Are we in the right orientation? It replaces radar. It's much more accurate. As we get closer, let's say there's a big rock in the way or a crater. We do the Neil Armstrong maneuver, which is to move sideways, which is called translation. That's what Neil Armstrong did. Before he touched down on the moon, he saw a boulder field, took control, and flew sideways, called translation. Then things get really dicey. As we get close to the moon, the lunar dust gets kicked up. Bits of rock and dust flying everywhere, and some of that rebounds back on the lander. We don't know how much problem this is going to be, but we're going to find out. It happened on one of the Mars landers, the Curiosity rover. They landed, they did a selfie, and there was rocks and pebbles all over the lander from landing. The engine exhaust caused that. Touchdown on Mons, Bhutan. Everybody in mission control jumps up, cheers and high fives and hugs, all that. We're down on the moon. Now it's time for Viper rover to do its thing on its own. It's on the back of our lander. We deploy ramps. Out they come. We have 2 ramps. Any idea why we have 2 ramps? If there's a rock in the way, let's say there's a big boulder in the way at one of the end of the ramps, a big boulder or a crater, we have a second chance to get off. Or maybe one of the ramps doesn't deploy. We have a way of getting off. Once that happens, once those ramps are done, NASA starts taking control of its lander in Mountain View, California. They do all sorts of communications tests. And then look at this. I'll show you again. Watch the rover. It's sitting low, raises itself up for better ground clearance. It's ready to drive off. So we're going to assume that, that the rover's all disconnected and ready to go. But we have to turn on cameras to make sure there's no obstructions in the way. So there's a front camera on that mast I showed you and a back camera. So let's say the front view is good and we're given the go to roll off. And now Viper is on the moon on its own. Again, dumb rover. It'll just keep rolling until it hits a rock. How do they avoid that? They have a driver and a co-driver at NASA Research Center. Their job is to steer the rover around obstructions. You can do that on the moon because the light travel time is only a few seconds. You can't do it on Mars because it's as much as 20 minutes. So if you'll notice the 2 people here on their screen, they're looking at the same camera on the rover. Vipers plan to have a 100-day mission going around. See that little pathway on the south pole of the moon there on Mons, Bhutan? That's just a starting number. The Curiosity rover on Mars had a 1-year mission, but because it was in such good shape, it's still going 12 years later. So Viper may be around for quite a while if everything goes well. Okay, now we go to work with the science. We stop. There's that big drill assembly in the middle of the rover. It digs down 3 foot, picks up dirt, and we have our bloodhound test. If there's water in that dirt, we will know it's there because hydroxyl atoms will be given off. Now it gets dicey. We're going into a crater that has no sunlight. If that's a solar-powered rover, how is it going to operate? It has a battery. So we'd go down into a crater. It's absolute darkness. With our headlight on, we do the same test. Dig down 3 foot, pull up the dirt, and sniff it. But because there's no sunlight, we have 50 hours, 50 hours, to do the work and get out of there. If we don't, the rover's stuck in the crater forever. Funny thing happens. While the rover's on the surface, the Earth goes away. The sun stays up, but the Earth disappears. Can't talk to Earth. So what the rover does, it stops, basks in the sun, checks its systems, and waits for the Earth to come back up. It's a really weird feature. While the sun is always up, the Earth is going like this, up, down, up, down. It's called libration. Just learned this the other day, a secondary payload, a little cube rover, shoebox size with 4 wheels. We're going to deploy it from the Griffin lander, and it's going to do some tests and just roam around and test some technologies. And one of the technologies is, can I survive the lunar night? On the moon, you have 14 days of daylight, you get sunlight, 14 days of darkness, no sunlight. We're trying to figure out a way of keeping a spacecraft alive. Closing comments. Okay, here we go. What's happening at Astrobotic is the beginning of a new industry, not just some space company. It's just like the first Model T coming off the production line led to a huge automobile industry. Same thing's happening in space now. Private companies getting into the business of building spaceships. Living on, working on the moon is a bad place. There's space radiation and particles, cancer risks, micrometeorite impact risks. Some meteors can cause major damage. When you're walking on the moon, stay out there for an hour at most, or maybe 2 hours, and that's it. There's too much risk. And also, you have to endure a colorless environment. On the moon, it's gray soil, black sky. That's all you got. No blue sky, no white clouds, no green grass, no ocean waves. Best way to deal with living on the moon, build shelters under piles of dirt. Moon dirt is the best way to protect against solar radiation, against micrometeorites. Plus, if you look in the upper right there, let the cube rovers I was describing do the work, the dangerous work. These little shoebox-sized rovers scurrying around like ants on the surface. They can do the work of astronauts and go in places where it's too dangerous for the astronauts. What's interesting is the moon has caverns just like the Earth. In fact, there's one cavern on the moon as big as the city of Pittsburgh. We might live there to get away from the solar radiation and dirt, and dust particles rather. Isn't that kind of weird? How did our civilization get started? We lived in caves. Now we may live in caves again on the moon and Mars for protection. Great place to do astronomy. We can build huge telescopes on the moon with only 1/6 the gravity and no atmosphere to look through. They're planning for some telescopes that will dwarf the ones that are on Earth. Also, the far side of the moon, the side that faces away from us, is the quietest place in the solar system. No radio noise, because the back side of the moon is all the cell phone communications and satellite channels are blocked. You have radio quiet zone on the far side of the moon. As I mentioned earlier, if we're going to go to Mars, do it from the moon. The Earth puts a big dent, a gravity dent, in the solar system. It's hard to get out of there. The moon is much lower density. We can take a lightweight spaceship and get to Mars. Come down to Moonshot Museum when you get a chance. In the upper left, there's a picture of Griffin actually being built. You see the guy in his bunny suit. We have exhibits and displays. It's the only museum in the world where you're allowed to look in a clean room, in a spacecraft clean room. Okay? Moonshot Museum. It's up between the McDonald's and the Wendy's on Allegheny Avenue. That's where I do a lot of volunteering. Thank you, and questions. Amateurs, our new slogan, or your bridge to the stars. Any questions? Test on Monday. Okay? Again, feel free to see me afterwards if something pops into your head. I'll be around. And with that, I say thank you.